So today's the day for our second session in this training course of ChEESE project. Today devoted to meteo-tsunamis, and it seemed that the tsunamis bring more attention. But I remember a comment coming from my colleagues in Puerto Rico that were saying, "Oh, Jorge, why don't you stop doing tsunamis and you go to meteo-tsunami that they happen every day in many parts of the world?" So as an application, meteo-tsunami is really a hot issue, a hot topic, and we see also not only in the Adriatic, also in Spain, that we have the events of these meteo-tsunamis. So for a long time, we decided to address these numerical modeling of meteo-tsunami with the code of the family of HySEA. But we need not only this having this idea in our mind, also having someone to do it. And now is Alex that is working with that in DTGeo and collaborating in ChEESE, that we have undertaken these tasks, and we have started with the development of a code of the HySEA family, this Meteo-HySEA. And luckily we have also we have the collaboration of Claire and her expertise in order to do that, because the main drawback for us was to be able to apply in real cases and to have the expertise of someone that have been doing meteo-tsunami modeling for a while. So and now that we are working together, I think we will be able to address this problem. And by the end of the ChEESE project, we will have a code for meteo-tsunami that is available, and it's probably operational if we are really lucky. But I mean, we are on the way. So today is the day to Claire will do an introduction to this meteo-tsunami modeling. She's really an expert on that. And in the second part, after the break, Alex will tell us what has been our work in this development, and will show us several examples in simple geometries, seeing if we are able to reproduce several phenomena that appear in this meteo-tsunami phenomena. And finally, we'll do some example in more realistic geometry, let's say nearly real problems. And the last thing that we have to address is to include the real atmospheric force in this model, to be able to do this task of a complete modeling of the meteo-tsunami. So that is the plan for today. Claire, I leave the floor for you, and thank you very much for being here.
Thank you, Jorge, for this nice introduction. So I will start basically with some generic concept about meteo-tsunami and what they are, and basically how we can use numerical models to represent them. So the outline of the presentation, so an overview of the generation process, because I assume most of you are from the tsunami community or the solid earth community, so you are not so familiar with the atmospheric processes, let's say. After I will speak about a bit, well, I would say quite a lot about modeling of the atmospheric sources. This is quite important. And some practical application. And as Rory said, it will be mostly in the Adriatic Sea because it's based on basically what I'm doing. So after that, we'll have the coffee time, and Alex will present Meteo-HySEA. I would like to say that if you have any questions or comments or anything, please do interrupt me anytime. It's better if it is a bit interactive, otherwise it's can be a bit of a boring lecture. So I really appreciate any interruption. Okay, let's go. So first, what is a meteo-tsunami? Well, I guess most of you know, but let's be clear. It's a long wave generated in the tsunami frequency range and driven by atmospheric disturbances. To simplify, it's a tsunami with an atmospheric source. This atmospheric source can come from very different kind of events. It can be from the weather-related events, but it also can be from acoustically driven events. So what are these acoustically driven events? Well, you all heard about the Honga-Hapai volcanic explosion, and it triggered an atmospheric disturbance, which was a pressure disturbance in this case, that actually managed to create what we will call a meteo-tsunami. So what are the principles for generating meteo-tsunamis? Well, we need a disturbance. So it can be a pressure disturbance or a wind disturbance in the atmosphere. And after, what we need is either the inverse barometer effects, and that works with the pressure disturbance. So this inverse barometer effect is saying that if you have the pressure going down, basically the mass of the ocean is going up. So this is the principle. So this is this 1 over rho g delta p for the elevation of the ocean. And otherwise, we have the resonance. And the resonance is basically, once we had the inverse barometer effect that is taking place, we can have another process that is basically when this small wave is resonating with the ocean long waves. And this is this ocean long wave, root square of GH, H being the depth, obviously. So this is basically easy, nothing specifically complicated here. All right, so let's start with the weather-related events, because they are, as Jorge was saying, basically extremely common. They are also, and I forgot to say that in the previous slide, an order of magnitude lower in terms of intensity than tsunami from other sources. So this is really something that is important to say, because we deal with really small waves compared to tsunami from other sources. Okay, so let's start with this transfer of energy from the atmosphere to the ocean, and with this offshore resonance principle. So we have two kinds of resonance. We have the Prodman resonance, and this is when the speed of the atmospheric waves equal to the speed of the ocean long waves. So this is basically, let's say, the most common generation of these meteo-tsunami waves. And we have also the Greenspan resonance, and this is the same principle, to be fair, but the speed of the atmospheric wave equal to the speed of the edge wave along a coastline. So this is the principle that, for example, the meteo-tsunami in the Great Lakes in US, they often have this Greenspan resonance. Okay, so that's for the idea of the resonance. And this other thing that is really, very important, actually, because as I say, these waves are an order of magnitude smaller than the tsunami from other sources, is that we have an amplification near shore. So what does it mean? We have specific locations that really are resonating, harbor resonance or shoveling or other processes that are really making this wave bigger. And this means what? This means that there are no location of interest for meteo-tsunami that can be life-threatening or actually capable of creating some, at the very least, flooding, or maybe some material destructions, infrastructure, destroying the infrastructure, etc., etc. And these locations are pretty much, look here in this map. This was a map done for the 2015. It was done, and this is all the events that were recorded, meteo-tsunami that were recorded. And hotspot locations are the Balearic Island, the Adriatic Sea, but the Great Lake in the US also, and there are other hotspots spread all around the world that are less studied, but it's picking up, basically. So, okay, I want to resume a little bit the principle. This is a really well-known figure. And just to say, you have basically some atmospheric processes that create an instability in the atmospheric layer. And you create disturbances, pressure disturbances, or wind disturbances. And through either first through the inverse barometer effect, here you create a first wave. And after, through the Prodman resonance, this wave is amplified. And after, through Scholing and Haber resonance, it can go from 0.03 meter to 3 meter. So that's the idea. And this is how we go there. This is a rough estimate, obviously, but this is to say that this is not something that it is a big trigger like a tsunami from other sources. Right, so now let's speak about what are these atmospheric sources, because I just say atmospheric disturbance, but what can they be, this atmospheric disturbance? So one of them is the atmospheric mesoscale gravity waves. This is basically what I just described before, unbalanced jet through the atmosphere, and that creates spontaneous balance adjustment. So this is really strong winds on the top of the atmosphere that create instability in the atmosphere, and there is a spontaneous balance adjustment, and that can cause rapid surface pressure oscillation. This is important to know that these mesoscale gravity waves, they can occur with any kind of weather. So it can be like during summer, when there is absolutely nothing that can alert people that wave will come. So that's really, these ones are very dangerous. And for example, when they occur in the Great Lakes, they are known to have killed people. So this is one of these things that are a bit different, let's say. And when we have the other kind, which is frontal passage and squall lines, that is definitely a storm, thunderstorm, forming along a head of cloud front, extending laterally for 100 kilometers. It's called derechos in Spanish. So this is long-lived, strong squall lines traveling many hundreds of kilometers associated with air pressure disturbance. And the last known is the tropical cyclones. So during tropical cyclones, there is the possibility to create some also atmospheric instabilities. So either through internal gravity wave or with the squall line-like characteristics that are formed at the edge of the tropical cyclones. So the animation that was running there. So on the left, you have basically an animation for the Adriatic Sea. This is the Adriatic Sea. And on the left, you have the atmospheric disturbance. It's a real disturbance, and you can see the disturbance here. And on the right, you see the consequences in the ocean. So basically, it's really small consequences for the ocean, because here we are offshore, and only because of the nearshore amplification, it can create flood. This event flooded some hotspot in the Adriatic Sea. So this was a big event at the end of the day. So okay, so that was just to illustrate somehow how this interaction between the atmospheric disturbance and the ocean are working, basically. So here you have another one. So you really have these waves in the atmosphere that create waves in the ocean. Okay. So now, what are the challenges in terms of modeling these meteo-tsunamis? Because this is really important. And the first challenge, and I would say this is the main challenge, is the difficulty to reproduce atmospheric sources with state-of-the-art atmospheric models. So these atmospheric disturbances, they are quite narrow. And as I said before, they can only be amplified in certain locations. So imagine if you have this disturbance in your model, but it's shifted north of the location that should be heated by the disturbance, well, you will have no meteo-tsunami at the hotspot location, which is a shame because you had the disturbance in your atmospheric model, but your ocean model is saying nothing is happening. So this is really something extremely important for the meteo-tsunami modeling is to take into account the uncertainty in simulating these atmospheric disturbances. And the second challenge, and this is really also a very, very big challenge, is that contrarily to other sources for meteo-tsunami, doing probabilistic hazard assessment is really tough for meteo-tsunami because we need to take into account climate change, which influences the recurrence and the intensity of weather-related events. So we cannot just take what happened in the past and infer what will happen in the future, because what will happen in the future will be strongly influenced by the climate and how climate change is going to change the recurrence and the intensity of these atmospheric disturbances. So this is really the two big challenges for meteo-tsunami modeling for the weather-related events. So now I spoke a little bit before about this, what I call acoustically driven events. And okay, as I said, they occur during supervolcano explosion or asteroid impacts capable of generated atmospheric acoustic gravity waves, including the LAM waves. I think everybody by now heard about these LAM waves because of the Honga-Tonga-HySEA explosion. And the speeds are far greater than the shallow water propagation speed. So this is really something that needs to be said, is that Brodmann resonance is not going to be the main driver of this meteo-tsunami. So what can we say? This existence of this meteo-tsunamis from this big explosion has been first hypothesized after the eruption of the Krakatau volcano in 1983, and confirmed with the eruption of the Honga-Tonga volcano. So there are the two same amplification processes. Nothing is changing, basically. We still have the deep ocean Brodmann resonance and the inverse barometer effect. So here, the curve that I'm presenting in the figure, there's a show that basically if the lump wave speed was divided by a factor of 1.5, we will have, or the amplitude of the pressure disturbance generated by the Honga-Tonga-HySEA explosion has been multiplied by 10. We will have meteo-tsunami surge above 1 meter, up to 10 meters, around 7% of the worldwide coastline. So what is kind of exciting here is that obviously these events, they are global. They are the long waves, they propagate all around the world. And in case of a really catastrophic event, well, we will have really other problems, but in terms of science, it's interesting to think that they can create really strong meteo-tsunami event of the order of other sources. So here at the bottom, you will see the animation of the Honga-Tonga-HySEA meteo-tsunami event. So on the top is the atmosphere, on the bottom is the ocean. And I just want to speak a little bit more of the LAM waves. So they are just propagating horizontally in the atmosphere with a speed close to the sound speed, and they are cycling the globe multiple times with surface pressure oscillation of several hectopascal per minute. There is processes of energy dissipation, obviously, towards the thermosphere, and that's basically the LAM waves in a nutshell. So in terms of the internal gravity wave generated by the complex eruption sequence, so yeah, this is the other thing, I'm sorry, I forgot to say, but there is not only LAM waves, there are also internal gravity waves generated by this big explosion, and with the Honga-Tonga, they were not so prominent, let's say, but they are with traveling speed between 240 and 217 meters per second, and they are largely controlled by the vertical profile of the temperature perturbation introduced by the eruption. So under favorable condition, large amplitude internal gravity wave can have speed favorable to the prominent resonance. That's a possibility. It's theoretical. Nobody has studied that yet. So this is all of this basically in terms of acoustically driven events. We have the data from the Hunga Tonga, Hunga Hapai event, and that's it basically. So this is really new and ready to be developed in the future. So the challenge is now for modeling this event. For me, still the challenges of understanding properly the acoustic gravity wave-driven atmosphere-ocean dynamics. I think it looks simple. It looks like we got everything, but I'm sure there are more to be said about it. Quantifying the uncertainties linked to the transfer of energy from the explosive process to the acoustic gravity wave. This is really challenging, actually. Having a continuous idea between the volcano explosion and the generation of this pressure disturbance is not something as simple as it sounds. And okay, climate change. Okay, I put it here. It's really minor, but it can impact the speed of the acoustic gravity wave because they depend on the Earth's surface temperature. Okay, so that's all I will say about this, let's say, acoustic gravity waves, or I will say really little further because really, as I say, this is a work in progress in terms of research. So now let's speak about the modeling of the atmospheric sources. So first, I will speak about something that it is at the edge of modeling. It's not exactly using any numerical model per se. It's a small model. This is called synoptic index, and this is only for weather-related events. And the principle is to identify in the atmosphere the condition favorable to meteo-tsunami event. And this is synoptic conditions extracted from numerical models and to correlate them with long-term record of sea levels at coastal station. So this is basically the exercise of like trying to link what are the important variables in the atmosphere that are generating this oscillation, this meteo-tsunami oscillation at the coastal station. The idea is to reconstruct the sea level time variation at a given coastal station, depending only on a combination of several wisely chosen atmospheric variables extracting from this numerical model. The advantages is low computational cost, definitely. No hydrodynamical model used, no need of HySEA or any other model. The drawback is that it's really a big approximation, okay? And there are a lot of false positives, and there is no possibility of using it for sonic boom for acoustically driven events. There have been several approaches used. The only thing that I can say about this here is that I think that the only place where the synoptic index was used for forecast was the Balearic Islands, and it was successfully used, I would say. Okay, so in terms of the data and technical requirements, obviously you need a tide gauge observation provided with at least 5-minute temporal resolution, and you need global or regional reanalysis products or observational data, but I would say much more models, and to create the synoptic index. So I will not go to the complexity of creating the synoptic index, but basically the idea is to correlate each atmospheric variable with the sea levels and to reconstruct the sea levels with different variables. Okay, so now more, let's say, into the core of the problem. deterministic models. So this deterministic model for weather-related events, the equations are based on the fully compressible Euler non-hydrostatic equation, scalar conserving flux form for prognostic variable, and the complete Coriolis and curvature term. In other words, the most complex equations are used in order to represent as closely as possible what's happening in the atmosphere. What is really important, sorry, is that to capture mesoscale gravity waves or convective clouds, cold lines, etc., we need to use what we call, I'm sorry.
Take your time, Claire. You need to drink some water. Please go ahead.
I'm sorry.
Don't worry. Don't worry.
It will pass.
Yes.
So this is really, really important, is that most of these processes that are generating meteo-tsunami, they are really high resolution processes. So the 12-kilometer global atmospheric model, they are now much more 5-kilometer, do not necessarily represent these processes very well. And so we need to use telescopic nested grid downscaling the global climate model to the high resolution, to the high horizontal spatial resolution, and I would say also vertical resolution. And this is the second point, is that we need a really high vertical resolution also, because we are trying to catch a process in the atmosphere, which is a process of unbalance in the atmosphere. And we need to have this vertical mixing of the atmosphere. So it's really important to have a really high resolution in the vertical also. Also, another thing, and this is really, really, really important here, is that we are speaking of frequency, tsunami frequencies. So we are speaking about what? Some few minutes, 15 minutes, less than half an hour. And we need to have basically output, I would say between 1 and 5 minutes from the model to force the ocean model. And this means that we need to have a very small time step in the atmospheric model to capture all the atmospheric processes. So this is really, at this stage, I would say, all these requirements are kind of telling us that we cannot use the models that our meteo services are using. That's really one of the biggest problems, because if we have like hourly output, we will not be able to generate any meteo-tsunami in the ocean with that. If we don't have enough vertical resolution, we'll not have the process that really creates the meteo-tsunami. We'll not have the disturbance, the atmospheric disturbance represented with enough intensity. So this is really the core of the problem here with modeling atmospheric sources. It's like really, we need to have really high resolution. And okay, so I said I will not speak about it, but I speak about it here. For the acoustically driven events, basically for the land waves, we can use really much more simpler models. So we can use rotating shallow water equation on a sphere. And this is really simpler models than for the weather-related events. And they are really much faster to run. And this is, let's say, less problematic. However, if we look at the internal gravity wave generated by the volcanic eruptions, this is a different framework, and this requires, again, very complex atmospheric model. But this is not done in detail, as I said before. So that's the idea here with the deterministic model. Okay, so I don't know if you remember, but at the beginning of this presentation, I kind of say to you, you know what, one of our main challenge is to have this deterministic model, really modeling the atmospheric disturbance at the right place and trying to get exactly the right intensity, the right location, everything. Well, so generally it doesn't happen. So this is when generally we need to use what is called surrogate models or emulators. And these emulators, basically, what are they good for? They are good for having this, taking into account this uncertainty of this atmospheric forcing. How it works? Well, basically, we kind of decide onto defining a disturbance. So in the Adriatic, it's a pressure disturbance with several stochastic parameters in time. So, for example, the amplitude, the location, as I said, the period, the speed. The speed is very important because, as you know, the Prodman resonance depends on the speed of the atmospheric disturbances. So this kind of stochastic parameters, after what can we do? We can have a prior distribution of them. And we run many simulations with the ocean model forced by this synthetic forcing. Then there are some, let's say, techniques to create the surrogate model. So polynomial chaos expansion, deep neural network, Gaussian processes. It is used also in the for tsunamis of other sources. So this is nothing like special. And after, it can recreate the extreme sea level depending on the input from the stochastic variables. So that's the idea, let's say, of the framework for the surrogate models. Their advantage is that they run pretty fast, and they can be used in combination with deterministic models. So let's say if I am not having enough numerical resources to have an ensemble of atmospheric model capable to represent the meteo-tsunami genic disturbances, atmospheric disturbances, I can run one deterministic model and use a surrogate model to kind of create this uncertainty after extracting the parameters from the deterministic model. I will speak about that a little bit later on when I speak of the practical use of all of these tools. Okay, so let's go to the last point that I want to cover here about this atmospheric sources modeling. This is climate modeling. As I say, this is something that is, let's say, secondary for other tsunami sources, even though not totally, but mostly secondary. And for us, it's really, in meteo-tsunami modeling, it's really like primary concern, because we cannot derive anything without knowing how the intensity and the recurrence of the meteo-tsunami will change in the future. So obviously, the idea is that climate warming is ongoing and deeply influences the atmosphere-ocean dynamics, including extreme events. And projecting the destructive potential of meteo-tsunami in the future is important for coastal communities already regularly affected by these events. So already this is this community in the Mediterranean Sea or in the Great Lakes, they have a need for knowing what will happen in the future. To be fair, this part is really a part that a lot of work needs to be done before reaching any conclusion concerning the impact of climate change on meteo-tsunami. But preliminary studies, I think 2 or 3, have already demonstrated that it can't be neglected. So the idea here is really the idea of the climate modeling community. It's the need to downscale as many as possible meteo-tsunami events at as many possible locations with as many global models as possible. So this is basically the exercise of trying to do everything. But as I said before, we need for meteo-tsunami modeling in the atmosphere really high resolution model. And we are not going to run high resolution model for 100 years. So this is not something that can be done. It costs too much. There are teams nowadays in the climate community that are doing great efforts in running a climate model of 4 or 5 kilometers in the atmosphere and the same resolution in the ocean. But as I say, it's not only the horizontal resolution. This is the time resolution, and this is also the vertical resolution. So even though this model exists, we'll still need to downscale them to properly capture meteo-tsunami events. So how are we going to deal with this idea of running really super high resolution models that are not meant to be run at the climate scale? Well, the idea is to use a global or regional climate model and to kind of detect which are the potential meteo-tsunami events in these models with the synoptic index that I presented at the beginning of this modeling section. And once these events are detected, we can only downscale these detected events. Well, if you remember, I said that one of the biggest problems of the synoptic index is that up to 60% of the event picked up by the synoptic index are false alarm. And in the reverse, not every meteo-tsunami event is picked up by the synoptic index. So the synoptic index is not yet, let's say, extremely reliable for this exercise. And this is just an idea of what can be done for climate change. And it's a kind of good idea with the preliminary requirement that the synoptic index should be improved. And basically how it goes, so it goes like this. So we will use, for example, reanalysis product in the atmosphere like ERA5. Design the synoptic index, for example, in the Adriatic Sea for certain locations. We look at an ensemble of climate model in the evaluation mode, and we check if the designed synoptic index capture the meteo-tsunami event in this evaluation of the models, of the climate models. If not, well, there will be some loops here. I don't know how long, how much. This is theoretical for the moment, but definitely there will be some iteration in order to get as much as possible the events that we can get with the synoptic index. After, we need to use this model, this atmospheric model at the kilometer scale or sub-kilometer scale. And once we get this model downscaling the chosen event, we can check if there are or not atmospheric disturbances. If there are atmospheric disturbances, we can go to the ocean part with Meteo-HySEA, for example. But also there is still the problem of, it's not because the atmospheric model has the atmospheric disturbance in it that it will be at the right location. So we will still need to use ocean emulators. So it's a big chain of uncertainty. So this is really like, as I say, this is really the biggest challenge, I think, for the meteo-tsunami community. So either we need more powerful computer, I don't know, exascale is not enough, we need more than that, or either we need to live with the certainty that the uncertainty is as big as what we know. So this is a bit just to illustrate that here with meteo-tsunamis, we have really grand challenges that are far from being solved in the numerical community. So that's that was a little bit the idea here of presenting this method, that it is, as I said, not bulletproof, far from. Okay, so now, as I promised, I will show some practical application of all these things that I presented. And I will start with something that has been around in the Meteo-Tsunami community for quite a while now. This is the early warning system. And here, this is not around for really long because this is in the Adriatic Sea, and this is like 8 years ago. And this is the idea here is really the classical idea of early warning system, numerical modeling, because we can forecast, contrarily to the other tsunami sources that are difficult to forecast, we can forecast what will happen up to 3 days, let's say, in advance in the atmosphere. So the core is to have numerical modeling and to be able to say 1 day in advance, for example, that we have detected in the model a disturbance capable of generating a meteo-tsunami. Obviously, we need observations. That is not because we have modeled that they are enough. We always need observation. We need a central warning system and also user-oriented product. To be fair, in the Adriatic, we stop at this blue box. We never went further because this is the products that need to be adopted by the meteo services, and they were not. So this is at the stage of the blue box. The green and the red box are not there. So I was speaking about modeling and the different nesting grid and everything. So this is an illustration in the Adriatic Sea of the complexity of what is done. So first, there are 2 different numerical modules. There is this module in green and the module in red. And the model in green is the one that is going to run for 3 days with resolution, as you can see, 15 kilometers, 3 kilometers in the atmosphere. So it's still pretty coarse. And 3 kilometers and 1 kilometer in the ocean. So obviously at 1 kilometer, we are far from the resolution needed to have flood or inundation, as described yesterday by Carlos and by Jorge. So this is not enough. So, however, this means that we have already the first step of downscaling the fields from, in this case, I'm using the ECMWF forecast, but it doesn't really matter. And here, the second module is actually the extreme event module, and this is where it's run only for a day and a half of forecast. And it's 1.5 kilometers in the atmosphere, and this is an unstructured, I'm sorry, Jorge, I'm using ATSERC, and this is an unstructured mesh in the ocean, up to 10-meter resolution at the coast. So it's, I'm not using the Meteo-HySEA yet. So this is end of the...
All welcome.
But obviously 10-meter resolution at the coast where we know that meteo-tsunami events can occur. It's really important. We need really to go down to resolution that are really low to high, sorry, for catching what's happening at the coast. Okay, so that's the first module, which is, let's say, the deterministic model module. And there is this stochastic module or a surrogate module. And this module is basically doing what? So from the module that I described before, the at-risk forecast, we just look at, we filter the atmospheric mid-sea level pressure, and we look if there is disturbances. So we look if there is this kind of disturbances, as you can see here, so Meteo-Tsunami M in event mode, or nothing, like here in silent. This detection is automatic. It's done with rate. This is the pressure disturbance rate spatial coverage. And this is just a criteria to define whether there is or not these disturbances. So until this stage, everything is automatic. So the model is running operationally, and the extraction is done automatically. Then things are a little bit more amateurish, let's say, because if we are in event mode, an email is sent to me, and I start looking at the results. I start looking at the result of the atmospheric model, and I'm checking how the disturbance look like. And you see this is the disturbance here for the atmospheric model. And after, to have a kind of hazard assessment, I use the surrogate model that I presented before. And this gives us a curve of elevation with a percentage of occurrence. And this is the first step, and this is happening like a day before any potential event. And this means that technically, a day before any potential event, a first warning can be released to the public. After a few hours before the event, I say 2 hours because the tide gauge that are the pressure sensors that are along the Italian coast, and the pressure disturbance are generally propagating from the Italian coast towards Croatia here. And here we can use these pressure measurements to kind of update the parameters that we put in the surrogate model, and to kind of update the final warning, and obviously to release it. So this is, again, I say practical application. It's half practical. It's still a lot to do before being, let's say, an operational tool used by meteo services. So this is just any way to illustrate how we can use everything I presented before into the context of doing something practical. Okay, now it's much more like on the research level. That's also practical, but much more on the research level. There are still a lot of things that we don't know about the generation of meteo-tsunami, including, for example, the impact of here in the Italian side, these mountains called the Apennines, and how they change the disturbance in the atmosphere. So one experiment was to remove the mountains. You can see here we have the mountains, here we don't. And the other idea, but this is more known, is to kind of trigger the Prodman resonance everywhere. So for the bathymetry of the ocean model, we flatten it at 50 meter depth. And so, as you can see here are the disturbance. What I call baseline is the normal orography and bathymetry. And here we have the 50 meter depth and in the ocean and the baseline. And here, this is the ocean result force with no Apennine. And basically, the conclusion of that is that if you look at the result in the atmosphere, there are changes, but they are not major changes. So removing the mountains didn't change the propagation of these atmospheric disturbances. And as you can expect, when we flatten the bathymetry, we'll generate really strong ocean waves here. So I don't know, let me see it. But you can see, yes, you can see the disturbance here is far bigger than here. So this is the idea. It's just a little bit of like using the numerical tools to play with the hypotheses that we can have. And this is one of the great advantages of doing numerical modeling, is that we can do nearly everything with a bit of imagination. And so we can test a lot of hypotheses. So that's one of the things I want to show you here, and please keep with me a little bit because this is a bit complex. This is the vertical profile along this transect here, where a meteo-tsunami occurred in the atmosphere. And this is vertical transect in the atmosphere. And basically, I want to show you how the sea levels that you see here, this is filtered, but this is real sea level. This is the wavelet analysis of these filtered sea levels, is in fact looking like the processes in the atmosphere. And here we have the potential velocity, we have the horizontal wind speed, we have the Freud number, and we have the vertical wind velocity. And you can see basically that here we have the mixing of the wind, for example, that I was speaking about. This is associated obviously with strong gradient of potential velocity, verticity, strong vertical velocities, etc. So that's the idea, is that thanks to this atmospheric modeling, we can also understand a little bit better what is going on in the atmosphere. And yet again, this is something that is important for us to understand these mesoscale processes and to really understand what's going on for the generation of meteo-tsunamis in the seas. So this is really extremely connected, these two processes, atmosphere and ocean. You can really see. No discussion there. And the last application, this is like a try of using pseudo-global warming. So pseudo-global warming is not real global warming. It's you can use it on short-term simulation, and basically the idea is just to add mean temperature difference. For example, saying, oh, it will be 3 degrees more at the surface of temperature. So we run 6 events in the Adriatic Sea, and we did this pseudo-global warming approach. And basically, we look at how it changed in the atmosphere, the atmospheric disturbance, and in the ocean, the ocean waves. And basically, this is a bit slow. Okay. Yeah, as you can see already, there are more disturbances in the future scenario. So you can see it here, they were not here. You can see it here. And obviously, it creates stronger waves in the ocean, no discussion there. And yeah, it's quite obvious from the animation that from these simulations that are not real climate change simulation, but pseudo-global warming, we do get increase in intensity of the meteo-tsunami event along the Croatian coast. So this is just again to illustrate what I explained before. This is really not generalized, and a lot of work is still needed to be done. So that's it. And I was pretty fast, actually. So I'm going to the concluding remarks. And after, I hope you will have many, many questions, but maybe not. So I would say that this is important to understand that the Meteo-Tsunami community is mostly composed of researchers from the observation side, and the numerical modeling component of this community is just emerging. And around the world, generally speaking, it is really something emerging. And there is an ongoing effort to integrate meteo-tsunami modeling within the tsunami modeling community. And there are major milestones that can be achieved, like defining common methods, model benchmark, creating common dataset for evaluation. This will improve definitely our meteo-tsunami model and create a worldwide numerical standards for meteo-tsunami modeling, because this is things that do not exist for the moment. Putting resources in common, improve the efficiency of deterministic operational model. and obviously going beyond the Meteo-Tsunami community, learning from the experience of the tsunami community. So this is, I would say, for me, coming from the Meteo-Tsunami community, things that I can see that will emerge eventually. And that's it.
Thank you, Claire. I see a question regarding the recording. I will distribute the recording after the sessions, probably tomorrow. Anybody else has any other questions for Claire?
And also the question that also was posed by email is the same that we see here now, that how is tall in Windows, and we don't we haven't done a course or a training or a video for that. We have installed HySEA, but just for Linux system. Okay.
Thank you, Jorge. Should we go into the break now then? If
Yeah,
there are
sure.
no questions?
Yeah, if there's no question, we could stop here, because like that, Alex can start from his part from the beginning, not need to
I
stop.
think, just sorry to stop you, I think there is one question in the chat in case you want to answer it before the break.
Yeah, let's.
Yeah. So, okay, I see the question about the fruit number as output. So this is for the atmospheric simulations. So basically, the fruit number gives an idea of the stability of basically the atmospheric part. And this is important. If you are really interested, I can eventually send you some literature about it. But this is basically the whole idea here is to kind of have these variables to track two things. First, how stable or unstable is the atmosphere. Second, how much this propagation is going to last, because obviously for the instability to keep propagating, we need to have the right conditions. So this is all about the atmospheric physics in this part.
For the numerical modeling of the hydrodynamical component, the fruit number also plays an important role, because it's related with the speed of the waves, that the shallow water waves, and so the flow is faster or slower than this perturbation. So if you have a supercritical flow, then all your information is moving forward. So it's also important for the numerics of the numerical scheme that you use. And if you are subcritical, then you have this information, this wave that propagates both, let's say, the upwind or downwind. So you have the possibility of propagating this wave, and so in many contexts, it's really important, this critical, subcritical, supercritical nature of the flow. Yeah.
Thank you, Jorge. Okay, then should we come back 4:15, so 4:15?
Okay, great.
Sounds okay?
Yeah, sounds good.
Okay, then I'm gonna stop recording and I will meet you all at 4:15.
And Alex, get ready for that.
Yeah, sure.
See you.
Okay.
Okay, so
go.
let's go with the second part of this course. This one devoted to Meteo-HySEA code. And Alex Gonzalez from the University of Malaga, and so is working for DTGU, but collaborating with the ChEESE project within the team of the University of Malaga. He has started to develop and to implement this new code of the family HySEA for Meteo-Tsunamis, and also started to test it, testing it. as I explained at the beginning, with some example in simplified geometries, and then with some synoptic atmospheric input, one of them in a realistic geometry. That is a benchmark for the National Tsunami Hazard and Mitigation Program of the United States. And now, from now on, the time is for testing and using it in real test cases. So please, Alex, the floor is yours.
Okay, so thank you very much, Jorge, for your introduction, and thank you very much, Clea, for the great introduction in this topic of the Meteo-Tsunamis. So as Jorge has said, I'm Alejandro González. I'm a mathematics PhD student from Malaga University, and I've been working now for more than 1 year and a half in this Meteo-Tsunami-HySEA code, which is a GPU-accelerated code for simulating atmospherically driven tsunamis on real bathymetries. So without further ado, let's dive into this last part of the presentation of this course. So about the code characteristics, here you have the model's equations. These are 2D shallow water equations in spherical coordinates with non-constant Coriolis force and non-constant atmospheric pressure. You can see here the equations. These are similar to the equation that Carlos showed yesterday, but there are some key differences. Here you have this term and this term represent the Coriolis force, okay? And this term is the non-constant atmospheric pressure. Here you have this tau theta and tau phi, which represents the friction. It can be a man in bottom friction, and the wind friction can be also included here. Okay, so these are the equations that Tsunami-HySEA resolves with the addition of these new terms. So about the numerical scheme, in a similar way as the HySEA family codes, Meteo-Tsunami-HySEA implements a 2D, high-order, but conservative, asymptotically well-balanced, finite volume numerical scheme. And just to explain, to elaborate a bit more on this asymptotically well-balanced property, it is related to the so-called geostrophic equilibrium, which is a steady state that occurs when the Coriolis force finds balance with the pressure gradient. It is well known that at large scales, geophysical flows are often perturbation of this stationary state. So by including this property in the numerical scheme, we can enhance the numerical results in a specific situation, let's say. So about the code implementation, Meteo-Tsunami-HySEA is implemented in CUDA language, thus leveraging on GPU-accelerated hardware. Right now, the code has 2 initialization modes. The mode 0 requires a topobathymetry file and an FCDF pressure file that will contain the several snapshots of the pressure evolution. Okay, so this mode is oriented towards testing real cases where you have a bathymetry, a topobathymetry, and a real pressure data. And the mode 1 is oriented, requires a topobathymetry file and a GRD file, which is an FCDF file, of a 2D pressure disturbance. And this is oriented towards laboratory experiments or handcrafted cases. Okay, well, this is the idea of this mode is that you define an analytic pressure profile as synoptic pressure, and you can perform the simulation moving that profile. Okay, and the inundation is computed following the wet-dry boundary treatment technique. So here I want to show you a very basic benchmark test in order to demonstrate that the addition of these new pressure terms works or is performed as expected. So this simulation, this test aims to reproduce the Proudman resonance. That is a phenomenon that occurs when the pressure traveling speeds match the water wave celerity, when there is a coupling between those speeds. So to run the test, we have a rectangular domain with flat bottom. The water is initially at rest, and we have a pressure disturbance that will enter the boundary, the left boundary, and will be moving to the right boundary. Here you have the pressure, the analytic expression of this pressure disturbance. You can see it's a function that depends on x and y. This analytic pressure disturbance is a one cycle of a sinusoidal wave with 1 hectopascal amplitude, 30 minutes period, and it's moving at 22.15 meters per second. Okay, so you can see here, it depends on X and Y, but it's essentially something 1D. Okay, so here I'm going to show you one simulation of this test where we set the bottom depth to 30 meters. And thus the water wave celerity is expected to be around 17.15 meters per second. And the pressure traveling speed is still at 22.15 meters per second. So here in the upper graph, this is a video. What you will see here in the upper graph is the pressure disturbance moving from the left boundary to the right boundary. The units here are pascals, 100 pascal, minus 1 pascal, minus 100 pascals. And in the bottom graph, you will see the water surface, the water response to that pressure. And the units here are meters. So here you have 5 centimeters, minus 1, minus 5 centimeters. So you can see there is, wait, it doesn't reproduce pretty well here this way, yes. So what we see is that there is an energy transfer from the pressure to the water surface. This energy transfer amplifies the water wave, but as the pressure is moving faster than the water wave, no, sorry, this one, apologies for that. That was a spoiler here. So what you can see, sorry, I reproduced the wrong one.
Yes, go ahead.
Okay,
No
okay,
worries.
so this one is where we set the bottom depth to 30 meters. The previous one I was showing is the bottom depth to 50 meters. So in this one, the pressure is traveling faster than the water wave celerity. So what we see is that there is an energy transfer from the pressure to the water surface. This energy transfer amplifies the water wave, but as the pressure is moving faster than the water wave, this energy transfer stops at some point. That's avoiding further amplification of the water wave. Okay, we can see here that the maximum water height was about 1 centimeter. And now this other simulation is when we set the bottom depth to 50 meters. So now the water wave celerity matches the pressure traveling speed. So now there is a continuous energy transfer from the pressure to the water surface. So the water wave is constantly being amplified. And we can see now that while in the previous case, the maximum water height was about 1 centimeter, here it reaches over 20 centimeters. So the water wave has been amplified over 20 times, thus reflecting the expected Brownman resonance behavior. Okay, so this test is just to show you that these very basic features are working as expected in our code. Okay, let's continue here. Okay, so now let's dive into the different modes to run a simulation. I will begin with mode 1, which I recall you that is oriented towards simulating, let's say, laboratory experiments. The idea is that you have a real topobathymetry if you want, or you can have an analytical bathymetry, and a synoptic pressure. So we are going to set up a simulation here in order to reproduce a real event that occurred in 2010 in the Gulf of Mexico. This is extracted from the National Tsunami Hazard Mitigation Program. Okay, so the idea is we can retrieve a topobathymetry, for example, from JETCO. Okay, when I speak about the mode 2, I will go into more details about this. Okay, so stick with me now. Let's assume we have a topobathymetry file. When we download a topobathymetry file from JETCO, we can inspect it, and these are the spatial variable and their names. Here we have the spatial variable latitude, longitude, and they have double precision. This is fine, but the elevation variable, it's called elevation, and the precision is an integer 16. So this is not fine. We need to reconvert this bathymetry to the proper format that Meteo-Tsunami-HySEA understand. Okay, so here I say we use a simple Python script to generate the appropriate bathymetry. I will do this in more detail when I talk about the mode 0, okay? But here you can see the correct variable names, X and Y, and double precision. But as I said before, longitude and latitude is also fine. But the elevation variable should be named Z and should be on single precision. Okay. So we already have our bathymetry in the correct format. Let's assume that. And we also need the GRD pressure file. So the idea is you have an analytic expression for the pressure. Here we're going to use this one. Okay, now this is a fully 2D pressure because we have the Y here and the S here. This is the profile of this analytic pressure at Y equals 0. It has a maximum of 5 hectopascal and a minimum of -1 hectopascal. So the idea is you have this defined around 0, 0, and we want to transport this pressure from point A, which is this one, to point B, which is this one. And we know that the time it will take to reach from point A to point B is 13.5 hours in order to reproduce this 2010 event. So what we do is create a GRD file, a raster file with the definition of this function. We use the nodes of the bathymetry we have just created in the good format and evaluate our function, this function, on these nodes. So doing that, we create a raster file that is the raster file that will be the pressure profile that will be transported along the traveling path. Okay, here in red you can see that in order to place the perturbation here, we have to do some mathematical transformations because we have moved the pressure to this point, we have rotated it, and we all have also added some curvature. This is not very hard, but you have to do you have to follow that procedure in order to have this. So the idea of this mode is that you have this pressure profile and you're going to transport it from point A to point B using a transport equation. Meanwhile, whereas in the mode 0, what you are doing is interpolating between 2 consecutive snapshots. So mode 1 is oriented toward laboratory experiments because you reduce the degrees of freedom by avoiding that interpolation. Okay, so that is the key difference between mode 1 and mode 0. That's why here you only need one GRD file for the pressure, one snapshot, let's say. Okay, so the last thing we require is the parameters file. Here you have the different parameters you have to provide. If you were here yesterday, Carlos went through the parameters file for the Tsunami-HySEA version 4.3.0 in very detail. You can see here that there are much less parameters required because this version of Meteo-Tsunami-HySEA is a very basic one. Let's say this is like a pre-alpha version or something like that. It doesn't include the nice features such as the nested grid system, the variable friction, the possibility of reading points from a TXT file. Okay, so this is much simple. So let's go line by line. The first line is the bathymetry name, which is this one. Okay, I call this. Then the next line is the CoE is asking you, the bathymetry data coordinates are in decimal degrees. You can select yes or no. In our case, is yes. If you select no, this might be because you want to perform some calculations in Cartesian coordinates. Okay, so initialization mode 1 is the one we are dealing now. The GRD pressure file to be transported, this is the one we have defined here. Okay, everything is 0 except for this region. Then you have to provide the position X and Y of the initial point A and X and Y of the final point B. Okay, now you have to provide the time for the pressure to travel from point E to point B. This is around, I don't remember now. Some hours. No, 13.5.
13.5, yeah.
That's right. Thank you. And then you can select the type of geometry to perform the simulation. 0 if you want to do it in spherical, 1 if you want to do it in Cartesian. Again, this is fine if you want to do some laboratory experiment. Now we are now dealing with spherical. Then you are asked if you want to apply the geostrophic reconstruction. This is related to the property I mentioned before, the asymptotically well-balanced property. We have selected yes because it eventually can enhance the results, but obviously the computational cost is higher. Then we have the boundary conditions, upper, lower, left, and right. We have left them open because we are dealing with something in the sea. okay? But you can put it on wall if you are dealing with, again, laboratory experiments. Then we have the total simulation time. This is set to about 20 hours, and we are saving time, we are saving the results each 10 minutes. Here we have the CFL condition. This is a stability condition. 0.5 is a very usual one. Then here, this is the epsilon H. Somebody was asking about this yesterday. This is a technical parameter in order to decide whether a cell is wet or dry. In this case, this number means that if the water height is less than 1 centimeter, that cell is considered to be dry, okay? Then you have this threshold to reduce the order of the geostrophic reconstruction. So if here we have selected yes in the applied geostrophic reconstruction, this threshold is to determine when you switch the order of the reconstruction. The reconstruction is order 2. So this 10 means that if the bottom depth is less than 10 minutes, then less than 10 meters, or in other words, if you are near the coast, you are going to switch to a one-order geostrophic reconstruction, and it is performed in order to make the code more robust when it comes to the inundation. Okay, 10 is a fine number. I've been testing several, and 10 is fine. Then you have the water bottom friction. This is fixed for all the simulation. Then you have the Coriolis parameters. If in less than 0, it will be a standard one, a non-constant. It means that it is going to be the 2 times omega times sine of the latitude, okay, where omega is the angular velocity of the Earth. So if you put here less than 0, you are going to get a Coriolis that varies with the latitude. And if you set a constant value greater or equal than 0, that is the Coriolis that is going to be set for all the simulation, a fixed Coriolis. And the gravity is similar. If you put less than 0, you get the usual gravity, 9.81, but you can provide a fixed value for the gravity in the case you are working with handcrafted test cases. Then the maximum allowed velocity of water, 100 meters per second. This is to avoid instability or to control the instabilities. Then you have the typical length, typical depth. When you're working with open sea, let's say you usually put here 1,000 kilometers. And the typical depth, usually one kilometer. This is to dimensionalize the system. If you're working on Cartesian coordinates, you usually put here 1 and 1 and so on. It doesn't matter that much. These are good numbers, let's say. And here you have the name of the simulation result. Okay, so in summary, this is the simulation we're going to run. The spatial resolution is 3 kilometers. Okay, delta X, delta Y. The number of volumes is a bit less than 1 million. The simulation time is set to almost 20 hours. And the simulation results will be saved each 10 minutes. So let me run this simulation very quick here on our cluster. Okay, so here I have Filcira. Carlos talked about this yesterday. We are connecting to the HP center, the same one as yesterday, called Zika. This is located in Sevilla and has several NVIDIA GPUs. So I have here everything we require to run the simulation. Okay, I have here the GRD pressure file, the topography file. We can connect to the cluster in order to see the remaining files. Give me a moment. So we can see, for example, that file, this one. This is the parameters file. The extension is .dat, but it could be .txt. Okay, so we can see it in order to know that I'm not lying to you. Okay, this is exactly the same as you have seen in the slides. Okay, the simulation. And the other file is the bash file that tells the Q system how to run this job. Okay, you put here a job name, and we are saying here that save this information of the simulation in this folder, and we are using GPU. The world time, this is 30 hours. This is a lot because the simulation is going only to last about 2 minutes. And here we say the Q system to go to this executable and use this parameter. This executable is the Meteo-Tsunami-HySEA code. Okay, this name is another one. I haven't changed it yet. So if we go here, SVATCH and the Gulf of Mexico SH, we have submitted the job to the Q system and it's running there. Okay, so we'll let it run in there and continue with the presentation. Okay, so now the mode 0 is oriented toward real test cases, where you have your topographic file and your real data from the pressure, okay, that is evolving in time, and you only have those data at certain times, let's say. So we can now work a bit more in detail about how we extract this topographimetry. Okay, so let me go to JEPCO. Here. I like to use the JEPCO datasets, but Carlos yesterday, for example, uses the Topo 1, which is also fine. Okay, we go here, download global coverage grids, and here we can use their application. We're going to go to this area of interest. Okay, we're going to select the area where we want. This is the Balearic Island. This is a hotspot location for meteo-tsunamis, and concretely here in Menorca. Okay, so what we have chosen the area we want, and we click here, the grid to the NetCDF file, we add to the basket, and see the basket, and download the data. Okay. So I have it here. And downloads, here I have it. I'm going to place it here. I'm going to extract it. Okay, I don't need this anymore. And here is the bathymetry I want. Okay, I don't need this anymore. I'm going to rename this to JETCO 2023 Menorca or Balearic Islands, and never mind. So we have our bathymetry here, just downloaded, but as I was mentioning before, if we inspect this bathymetry, we can see that this parameter is not well defined, okay? The precision is not the current one, and the name is not the correct one. So we need to convert it to the proper format. So to do that, I have a Python code here, a very straightforward Python code. Here, okay, I have the bathymetry file named here. And with this code, I read the points from this raster. I open this raster with this module. I retrieve the elevation. I close it because I don't need it anymore. And with this function, I pass it the spatial coordinates, X and Y, retrieved from the raster, and the set value I have retrieved. So, and tell it to generate this file. Okay, this function, GRD write, you have it here. You can scroll slowly if you want to see it later in the video. But essentially, it just creates this GRD file, which is essentially a NetCDF file, and add the values. But it has now the correct convention, naming convention. Okay, so let's run this. Okay, shouldn't take that long. Okay, so now here we have our good bathymetry. I'm going to load it in ArcGIS just for you to see it. ArcGIS is a good software for dealing with raster files and shapefile, vector data, and so on. Okay, so here you have it. This is our brand new bathymetry we have just converted. Okay, so let's leave that there, continue with the presentation. So we have the topographimetry. We require now the NetCDF pressure file. So what does the NetCDF pressure file must have? It must have a single precision variable called time, which contains the number of time steps of the pressure evolution. For example, if there are 20 time steps, the variable time is a list from 0 to 19. Okay, these are the time steps, let's say. Then you have the x variable called x or long, doesn't matter. The y variable, double precision both, called y or lat. And then you have a single or double precision variable called p, which depends on time, y, and x. So this is the spatial distribution of the pressure disturbance at time step time. Okay, so at each time step, you have a spatial pressure distribution, which is essentially defined within this variable p. Okay, so I'm going to show you an example I have here. Here in our ChEESE. Okay, so I have this pressure, this one I have crafted myself in order to demonstrate this. Okay, but let's assume this is a pressure file you have from your real data. So this contains 11 snapshots. I'm going to show you these snapshots here. Okay, in mode 0. I'm going to not show that. So this is the pressure. The first step is everything's 0. Okay, but the consecutive steps is this sign pressure moving from here to up here. Okay. Okay, so you can see they're moving. And so if we go back here, so let's assume we have the NetCDF pressure file, but we are not sure if it is on the correct format. If by correct format, I mean the variable's name. You should know that you have these four variables: the time, the spatial variables, and the one which depends on time, y, and x. But you are not sure if the naming is the good one. And also it's likely that the number of cells and the spatial resolution does not fit with the topobathymetry file you have just created. So I'm going to show you a Python code that performs both things at once. Okay, so going back to PyCharm. I don't need this anymore. So here I have my pressure file. This is the sign test with the 11 snapshot. This is the boot, but no, this is the boot bathymetry file, this one. From this bathymetry file, I'm retrieving the spatial coordinates. I'm calculating the spatial resolution, delta x, delta y. And these functions interpolate the values of the badness TDF into the points extracted from the bathymetry. So it interpolates into the right points and change the naming of the variables in case that they are not the good ones. Okay, so this function take the bad pressure file, this minimum longitude, maximum latitude, minimum latitude, maximum latitude, delta x, delta y, and generate the reinterpolated sign pressure with the good naming convention and on the proper points. Okay, so let's run this. Shouldn't take that long. Okay, so here I have it. This is the file I need, containing the several snapshots, and this is the good topobathymetry. Okay, so now to run the simulation. To run the simulation, well, in this screenshot, you can see the good naming convention for Meteo-Tsunami-HySEA. Okay, the time is a single precision, the time steps, the x and y spatial coordinates, and this other variable named p that depends on time, y, and x. And the units are pascals, which I haven't said it, and it's very important. Okay. So the NetCDF we have just created is on this format. And just the last thing we need to define in order to run the simulation is the parameter file. So this is everything similar as the mode 1. But now when we select here the initialization mode, we put a 0 here. So if we put a 0 here, the code asks which is the NetCDF pressure file with the several snapshot. This is the one. And we have to provide the time resolution of the NetCDF pressure file because the time variable that includes this NetCDF is only the time steps. It doesn't, so we need to provide the time elapsed between two consecutive snapshots, okay? Of course, this is assuming that the snapshots are equally distributed in time, okay? So we're saying here, this is the delta T between two snapshots. The rest is the same. We have set here a total simulation time of, and this is like 8 hours. We are retrieving results each minute, and the other things are the same. Okay, so in summary, we are going to run a simulation with the resolution. This is like 15 arc seconds. The number of volumes now is over 1 million. The simulation time is about 8 hours, and we're saving time results each minute. Okay, so let me, before going into the post-processing results, let me try to run this simulation. So let's go back to FileZilla. A new file should appear here. This is the result from the previous simulation, so I don't need this anymore. Here I have the files required for this new simulation. I put them here. And so I'm gonna go here and let's see this file. Okay, this one is the same as I have shown you in the slide, okay, with this GRD and the CDF. And then we have this other file, which is the one that communicates with the queue system. Okay, again, here we are calling this executable and passing this parameter. Okay, for init type 0, this is the good one. So let's run this. Swatch, I don't remember now. This one. Okay, let's run it. And it's going to run for a bit. This take a bit longer than the one before. So in the meantime, we can talk about the post-processing the results, about the visualization of the 2D simulations. So you have two main options from my point of view. One is using the NC view that Carlos used yesterday. And you can also use Python. Carlos, with these libraries, NetCDF4 and Matplotlib, essentially with these two packages, you can draw almost everything. Okay, Carlos used yesterday the GDAL library, which is also a very good one, but I know that an advanced use of that. Okay, so we can, for example, a very straightforward visualization mode is using NCView. So we can go here to the cluster. We have our simulation, which is this one, and we can do here just NCView results, Meteo-Tsunami, Gulf of Mexico. Okay, so here it will be open, will pop up a window. You can see here the variables that the code provides. I have to say that this one and this one does not work yet. It's not implemented. As I said before, this is a very early version, but you can see here, for example, P is the pressure. This is the pressure that is being transported from point A, which was about here, to here, point B. You see there is just being transported by a transport equation. Okay, this is not very interesting, but you can see there that everything is working fine. And what we are most interested in is the water-free surface. You can have here you have here also the velocity at the water-free surface. We change here the range. Let's say minus 0.2, 2.2, 0.2. Okay, let's go to the first frame. And you can see there the evolution of this water-free surface from the pressure disturbance. So here you have a Meteo-Tsunami wave. From this zone, this area more or less occurs a Proudman resonance. That's why we are interested in reproducing this event. And so yeah, you can imagine the rest. It takes a bit long to show every frame. Okay, but we can see here the simulation as well in Python. Okay, I'm gonna close that. Here in Python, I have created a video using this library in NetCDF4 and Matplotlib for the same simulation. Okay, so you can see that the results are the same. Now that depends on whether you want to use the NCView, the Python library, or maybe you are used to another visualization tool. Okay. Okay, about extracting time series. Again, if you want to use Python, you only require these two libraries. If you want to use NCView, this is also very easy because you can here open again NCView. It's very easy, but it's not very precise, let's say. Okay, you can select here again these ranges. this, and this. And let's say you want a time series. I'm going to amplify. You want a time series here around this point. You click there, and a window pop up with the time series. So it's very easy. You can also, for example, dump these results into a TXT file to download it and portray them in Python, for example. So this is a good way to visualize the data without the need to download them. Okay, of course you can apply your Python tools in the cluster, but I use them on local, so I usually have to download them. Okay, so yeah, with Python it's the same. You only have to use these two libraries, which are very easy to use, I would say. And finally, if you want to visualize 3D data, this data in a 3D space, which is can be very fancy and very nice, you can use again NetCDF and Matplotlib. I want you to take home that these two libraries are sufficient for drawing everything. But for example, you can use also ParaView. ParaView is an open source multi-platform data analysis. It requires at least for you to see some tutorials in order to start using the tool. But you can create simulation very, very cool like this, okay, where you have the pressure here, the pressure layer. You can see it's a bit laggy because it's in presentation mode, I don't know why. But you can see here is pretty cool. Okay, here you have the scale in the pressure and the water surface. Okay, so that was all, but before finishing, I'm going to show you the simulation results for this last simulation. Okay, so let me go here. Have it ended? No, it has not ended yet. We can see here. Okay, let me go to FileZilla. I'm going to cheat a bit and get the results I have here, because I have one. I'm going to name it to solve2. Okay, this is exactly, let's say, the same result. So I have it here, and I'm going to visualize using NCView results, MT Menorca, solve2. Okay, here we have it, and here I have it. So here you can see the pressure. The pressure, if you remember, was 0 at time step 0, but then it is a sign pressure moving. So you see there, this reminds more or less like a worm crawling. And this is an artifact due to the interpolation between two consecutive snapshots. Okay, so of course, this test would be better if I just transport this sign pressure from point A to point B, but I wanted to interpolate between snapshots in order to simulate when you are dealing with real data. Okay, as you can see here, an artifact of this interpolation, a linear convex interpolation. And you can see here the water height results. This simulation is not the best one. It's something I just come up with. But what you're seeing now is the water-free surface. Okay, this mode is not the one preferred for these kinds of simulation. Okay, but we want to test this with real data and see what happens. Of course, the better your time resolution is, the better the results you have. Okay, so I guess.
Can I ask you about this interpolation artifact? Is it like does it depend on the time resolution or on the space resolution, or what's how do you avoid having these artifacts?
And the way to avoid this artifact is, I mean, this example is what I want is to move a pressure profile along a traveling path. So what I should have done is use the other mode, because the other mode applies a transport equation. But now I'm interpolating between two positions of this path and created this artifact. But if you're using real data, I think that wouldn't happen, but we haven't tested it yet.
Right,
Mm.
I see. Okay.
The idea here was to go further and to try to mimic what we should do in the case of real
Yeah.
data, but not doing with that and doing something similar to the other example in the Gulf of Mexico that I don't know if you mentioned is a test, a benchmarking test from the NTHMP, so that we took to test the code,
Yeah.
and so the thing is that this mode is ready to use the data from observation or from an atmospheric model to be the input to HySEA code.
Yeah.
Exactly.
Okay,
Exactly.
okay.
Exactly. I haven't
Thanks.
said that that was a benchmark, the National Tsunami-HySEA Mitigation Program. I haven't shown you the more results, but yeah, we are happy with those results, I would say. Okay, so that's will be everything from my part. As you can see, some key features are missing, like the nested grid system, the variable friction, and so on. Our priority now is the inclusion of the nested grid system because a Meteo-Tsunami, as Claire has mentioned before, is something that encompasses several scales. So it's mandatory to have a nested grid system in order to properly capture this behavior. So yeah, but we're working on that.
Clear. Here we have a question from Chile, from Cesar, that is asking, is not clear how to and where I can get the pressure file.
Yeah,
I guess that Cesar
don't
is
know
asking
neither.
no, I think that Cesar is asking in real cases. No, that the reason I addressed the question to Claire, not to Alex.
So, okay, so this is really like, I tried to convey that in my presentation before, is like you need to have a model, you need to have an atmospheric model to create your simulation, because as Alex demonstrated really quite nicely, when you interpolate between fields, you will create artifacts. So you need really high resolution, temporal resolution fields to force meteo-tsunami simulation, which is always a big problem, really. So finding these fields from the meteo services, no, it's impossible, because the meteo services will provide them at 1 hour, maybe 10 minutes maximum, but that's it. So the suggestion is to collaborate with atmospheric scientists and to have them running their model at a higher time resolution.
Okay, thank you, Claire, for your answer. Any more questions from the audience? Any other question that you may?
I can ask another question, just a curiosity. You mentioned that you can use ParaView, and I have some experience with that, but I was just wondering if can you use straight like the output from HySEA, or do you need to modify something before using it, before importing it in ParaView?
No, in ParaView you have the option to read the net
Yeah.
CDF file. Of course, you have to know which option to select in order to read the file.
Yes.
But
Yeah.
it is straightforward. Let's say you don't have to do anything weird.
Okay, because there's usually like a few types of NetCDF readers, and okay.
That's right. That's right. But
Right.
there is one that accepts the HySEA output.
There's one that works.
Yeah.
Okay, thank you.
Okay. So some more questions. Otherwise, I think that today we were shorter. We did 1 hour and 1 hour more or less, and so we finished at 5. That's very good for me because I must go to pick my boy from school, so it's great. So thank you to the speaker. And if you don't have any more questions, I don't know if Maria Jose has something more to say.
No, I just want to thank the trainers and the attendees as well. And like I said before, I will send the recording and the presentations. Please send me your presentations to the trainers. Don't forget. And well, stay tuned for more training sessions like this one in our website in ChEESE. And that's it from our side.
Okay.
Thank you all.
Okay, thank you very
Thank you.
much.
Thanks for the nice course.
Bye.
Thank you.
Thank you.